All right, we're in Power Focus Area 3, Objective 2 slideshow, moving on with wave basics. So we'll get right to it. All right, so mechanical waves are defined as any waves that have to use a medium to travel through. So for us, almost every wave we think of would be a mechanical wave. We're talking water waves, waves that are made by a rope, a sound wave. There are some waves that are not mechanical. They're called electromagnetic. We'll get to those in a minute, the most common one being light. So there are some waves that don't need a medium, but any wave that has to pass through something. Remember, a medium is something like water that moves, the energy moves through. It's called mechanical waves. And the way they work are the particles in those mediums and the waves are vibrating. The energy from the vibrations in the mechanical waves hits the particles in the medium, like the water, causes them to shake or oscillate back and forth. They bump into the next water molecule next to them and transfer the energy and make those shake. And then the next one and the next one and the next one, and keep transferring energy that way. So the medium is transferring energy, not transferring the wave itself. Mechanical waves travel, think of them like dominoes. If you have a whole bunch of dominoes lined up and you tip one over, well, it hits the next one, and the next one, and the next one, and they keep falling over. Same idea with the mechanical wave. The energy from the wave hits the particles in the medium, and it hits the next one, and the next one, and so forth. The further the particles are spread out, the longer it's going to take, and that's going to matter a lot when we're talking about the different states of matter for a medium. So here we go. A medium, we said, is what the wave travels through. If you look down here, we have some common examples of air, water, particles, strings, solids, liquids, or gases. And those are where we're going to focus most of our time today, or the first half of today. If you look at these pictures, this is showing like the particle level. Like we're looking at the individual atoms within a solid over here on the left. And if you notice the particles, they're very closely packed together, which makes sense. You can't put your hands through a solid. Liquids, we notice that in the middle, here, there's some spaces in between there. So if I were to put my hand in here, there's enough space where the water molecules, the liquid molecules would move around me. And then in gas, over here, there's a lot of space. Well, look at what it says for the bullet point. Waves travel fastest through solids and slowest through gases. And it asks why. And it's all about how those particles are arranged. So if here comes a wave and it hits a solid, it's going to transfer energy and make this thing start shaking back and forth. Well, it's going to hit what's right next to it and right below it, and it's going to keep transferring that energy quickly because everything's so closely packed together. When that happens in a liquid, the wave hits this molecule. Now it has to travel a little bit of space before it gets to the next, and a little bit of space before it transfers the energy because those particles aren't so close together. So the energy travels, the wave travels a little bit slower through the liquids. In our gas, you can clearly see if the wave hits this particle and transfers its energy, it's going to have to move a lot further before it comes in contact with another particle. So waves are going to travel the slowest in gas because their particles are spread out, and waves will travel quickest through solids because their particles are closest together. Some common examples of mechanical waves are ocean waves, sound waves, earthquakes, and we'll talk about the difference between these two shapes and types of waves coming up here briefly. All right, the one type of wave that we said is not mechanical, does not need a medium, are electromagnetic waves. Light waves are the best example, but if you look at the bottom of the screen, there's radio waves, microwaves, ultraviolet, X-ray. There's several different electromagnetic waves, and that actually will be our next entire focus area. We know light can travel through outer space, and there is no air in outer space, so that's kind of proof that they don't need a medium, but they can also travel through medium. You can see light in water, so it can travel through mediums as well. All right, the rest of today's slideshow will be talking about the difference between transverse and longitudinal waves and how we can tell that difference by different methods, by definitions, by sight, things like that. We kind of already said there's also a third type of wave that won't be on our content assessment, but they're called surface waves. We'll get to those briefly, but again, don't focus on those. You don't need any notes on the surface waves. All right, so longitudinal waves. The beginning of that word itself helps you kind of maybe remember what it looks like because that word starts with long. So let me get back to the arrow and my animation continues. And if you look, these are left to right movement. It says, look at a single pulse. Well, a pulse is these up and down waves here. I'll highlight one of them. If you kind of see like this area where there's a whole bunch of particles up and down, here's one, here's one. Let me get back to the arrow and watch just the one and see how it moves. It's moving left and right, side to side is how they're moving. Look at an individual particle, like one of the red dots on the screen, and they are also moving left and right, back and forth. So longitudinal waves, that's how the particles move, left to right, side to side, and the fancy word for that is parallel. And you can see all these up and down pulses are parallel to each other. You really don't even need to pause this or slow this to see how the particles and pulses are moving here. They're moving up and down. And in math, if I look at, here's my kind of base or bottom point, and they're moving up and down, well, when they meet like that and make little nice 90-degree angles, that's called perpendicular. So the particles in transverse waves are moving up and down, or a fancier way to say that would be perpendicular. Surface waves are kind of crazy. They move up and down and left and right. And if you watch one of those yellow dots, it ends up back where it starts. So it's going up, down, left, right, but they kind of end up back where they start. And water is a great example of a surface wave. So the definition, which you definitely want in your notes, of longitudinal waves is that particles move parallel, back and forth, side to side as the wave. So the big red line on the left here, that's the wave starting. And if you notice, the particles are moving left to right or parallel. Transverse, oops, I'm sorry, skipped ahead a second. Another word you don't definitely need for your assessment. Longitudinal waves are sometimes called pressure waves or compression because they get pushed in and out. So you might see a picture that looks like this, kind of like a spring being stretched and pushed together. Just realized if it's long and the top part of the wave and the bottom are parallel to each other, then it's going to be longitudinal waves every time. Now to the transverse waves. We said the particles will move up and down like we see in the picture there, and another way of saying that is perpendicular to the wave itself. So the wave comes in like this, up and down, and that causes the movement of the wave to be, the energy transfers as up and down or perpendicular movement. A good example of a transverse wave is a light wave. All electromagnetic waves like the X-rays and gamma rays and microwaves are transverse. I don't know if I said it earlier, so I'll say it now in case I didn't. A good example of longitudinal waves are sound waves. They compress and go in and out. If you've ever been next to a really loud speaker, you can kind of feel that hit you in and out. Like we said, surface waves will not be on the test, but the movement of particles is up and down and left and right. So kind of quiz yourself here. How do particles in longitudinal waves move? Well, they move parallel or back and forth or left and right. Transverse, that's right, they move up and down, and the fancy word for that is perpendicular. Sound waves, well, look, those lines would be all parallel to each other. They would move left and right, in and out, so that would be a longitudinal wave. And electromagnetic waves, if we look at the picture, they're going up and down, so that would be transverse. And that's the whole objective, so hopefully that'll help us pass our content assessment.